All right. So geometric vector had no fixed location. So even when I was teaching it, I would say, okay, here's the vector, and then I would grab it, and then I would just move it around, right? You saw me do that, right? As long as I don't change the size or the direction, orientation of it, then it was the same vector. So you've seen me do that. An algebraic vector, we're going to always try to get that tail to be at the origin. So you will predefine a system, some sort of coordinate system, and then you would place that vector. So let's say if you had, two-dimensional space with x and y axis, you're going to grab this vector over here and actually move it so that the tail is right at the origin. Okay. Next. We're going to be learning how to convert vectors from algebraic form to geometric and vice versa. So I have 4 examples here. I'm not going to do all of them at once, but I'm going to utilize these grids. So this polar grid where you have concentric circles, we're not going to study too much of that, but I wanted you to be aware that there's different types of systems that you could record. And so these values right here where you have a single number that doesn't have a degree symbol, so this would be the magnitude, and then you have an angle. This is going to be the direction, but this direction is going to be the mathematical direction, not like bearing. So this is math way of quoting angles, which was from positive x-axis and is going to go counterclockwise. So I'm going to attempt to draw this 120 degrees. Okay, so on this circular place, we can actually easily locate 120 degrees is right here. And I need to go out 5 radii. So that's 1, 2, 3, 4, 5. Place my arrow right there. So that's my vector. It's supposed to be nice and straight. I apologize, it's not. This is the vector. What did I call it? Vector U. Okay, so this is vector U being drawn. Now, for me to convert this vector to be in the other Cartesian form, I would move it to the origin. Oops. I mean, it's not going to be precise. And you can kind of estimate where it is vertically and horizontally. Okay. Now, estimation is not the greatest thing. We want to actually find the precise version. So I'm going to show you how you can actually think about it to get the precise value. So I'm going to draw the right triangle on this original picture here. And I'm going to highlight the one that's horizontal, and I'll place the value right there so you can follow along. And this vertical, I'll place it over here, and then I'll do something with it. Okay, so we know the size of the hypotenuse only, and we know the angle over here is 120. What would be the angle on the inside of this triangle? Who would like to unmute themselves and tell me?
$60.
60, very good. Oops. So this is angle 60. Now, because this is a right angle triangle, because it's purely horizontal and vertical, we can use SOHCAHTOA to figure out what the yellow one will be in terms of the 60 angle and the 5, right? Except, do you see how this yellow thing is going left? Because it is going left, we're going to use a negative, okay? So I'm going to say, because I want to use the 60 and the 5 and the yellow, that means I'm going to use ka. So let me write down above this, I'm using ka, meaning cosine of 60 is equal to adjacent, which is the yellow thing, right? Except I'm going to have a negative on it. And I'm going to have the hypotenuse. So this is the adjacent over hypotenuse. Right? So for me to solve for this yellow part, I would have to say that, let's call this yellow part actually, I'll keep it with a question mark. So the question mark here would be 5 multiplied with cosine 60, except there was going to be an extra negative there because it went to the left. Now take out your calculators, and can you try to type in 5 cos 120 instead? What do you notice? So compare typing with a negative 5 and then cos 60, and then without a negative and type in 5 cos 120. What do you notice? Same or not same? They are the same. And that's why mathematicians decided, for this reason, they said, well, because the cosine function is actually going to give us the negatives when we need the negatives, mathematicians said we're going to start our 0-degree rotation on the edge here. So do you see how there's zeros over here? Instead of like in bearings, we would have 0 up here for the north line. So in physics, you do it kind of in a different way. So because the 120 will actually give you what you want. Okay, so let's do the same thing for the blue one. So now notice the blue one. The blue one is going up. Because it is going up, we're going to use positive. If it went down, we will use negative on it. Okay, so we'll have positive on this. And this is going to be, because 60 is over here, so it's going to be opposite over hypotenuse. So that would be this question mark in blue is going to be sine of 60 is opposite over hypotenuse, which is 5. And so if you were to isolate this question mark, you would have 5 sine 60. But you can also have done it with sine of 120. Can you verify that this will yield the same thing again? Type in 5 sine 60 and then 5 sine 120. Okay, so if you verified it, that means it's working. So that won't matter where the orientation is. It's going to actually provide you with the right things. For example, let's take another angle. Okay, so if the angle, let me draw different ones just to prove to you that the mathematicians are actually pretty smart to choose the angle to be 0 over here and going counterclockwise. So let's say the angle was 140. Okay, so here that means if we were doing the horizontal, so horizontal is still left, but going vertically is going to be down. Okay, so I'd like you to do cosine of 240 and verify it's a negative number. And then sine of 240, that is also a negative number because this is down and this is to the left. Yes or no?
They're not the same number, but they're
That's
negative.
okay. Then it's about negative or not. Okay, and then let's try another one. If you were going this way, so I'd like you to verify here, you were going to the right, so that's positive, right? Going to the right is positive. Oh, my computer went black for a moment. Is it back to projecting to you?
Yes.
Except my pen is not writing. Let me restart my OneNote. It's happened a few times before, didn't it? Okay, so here you will going to be to the right and then down. So going to the right, it's supposed to be positive. So cosine of 300, let's type in. It's supposed to be positive because you're going to the right. Test it out. And then sine of 300 is supposed to be negative because you're going down. Is that true? Verify. They won't be the same numbers again, but just positive versus negative, okay? So every time we actually quote angles in algebraic fashion, we're going to be quoting them from the positive x-axis in this counterclockwise notation because it's going to give us the correct sign. So we don't have to, say, oh, it's negative here because it's going down, it's going up. We can just type in the proper angle and it's going to give us the sign that we need, okay? So based on what we just did, this yellow piece right here, is exactly what number, roughly, actually? It's okay if you round. Can someone tell me what that yellow piece was?
Negative 2.5.
roughly negative 2.5. And so this is negative 2.5. Look at our coordinate grid on this side, right? You're going 1 square, 2 squares, and it's just a little bit off just because of the way I drew it. It's probably supposed to be more like this, right? But it's supposed to be right in the middle. It's just my picture is incorrect. And then the blue one, where's my blue highlighter? What was 5 sine 120? What is this length here? What did you guys find? What number was it?
4.3.
Roughly 4.3. So you can see how there's 1, 2, 3, 4 units and just slightly higher there. So it's actually giving us 4.3 here. Okay, next thing I need to talk about. So when we have vectors that are being quoted now algebraically, what we predefine is we predefine a basis vectors along the axes. Okay, so the x-axis will have a unit vector. So I'll do a little arrow here. Size 1, remember when we talk about the unit vector, so I guess I could say unit basis vectors, along the x-axis. We're going to use I for that, and we're going to use a little hat on it to indicate its unit. So if I had U with a hat on it, that will be size 1, okay? But we'll be using specifically letter I for the direction in the x-axis. We will be using a little j for the direction going in the y-axis. So actually I have it on the bottom here. So when we extend to 3 dimensions, we're going to be doing it in, well, we're going to try our best to draw 3 dimensions. It's going to be 90 degree here, 90 degree here on the bottom, and 90 degree this way. So I don't know if you can kind of imagine that this arrow is pointing out at you, and I'm just trying to draw it in perspective. Okay, so the I vector is going to be size 1, pointing in the positive x-axis. So this will be the x-axis, and then I will be pointing in that direction. Then J will be along the y-axis, so y-axis will be going this way, J, and then Z could be pointing out at you. So we will call that K hat. So we'll have 3 unit basis vectors that they're just pointing in the right direction of the orientation of your axes, okay? So we won't do the 3 dimensions yet. Okay, let's start with 2 dimensions. So how do we use these vector units to create vector U? Do you agree if I were to take the vector J and stretch it? So imagine I took J and multiplied the J vector by 4.3. So if I were to multiply it by 4.3, it's going to actually stretch out all the way to this edge here, just like the blue region was. Then if I were to take I and multiply I by negative 2.5, I'm going to take the I, because this negative is going to go in the opposite direction, and it's going to be exactly the length of this yellow one. Now, what does that mean? If we take this negative 2.5 I hat plus 4.3 J hat, and the hats, remember, instead of writing down a little vector symbol, it just basically another way to indicate that it's a size 1 vector, okay? So if you would prefer to continue writing vector symbols, you can, but then you would have to say size 1 every time. But if you use the hat, you don't have to say size 1 beside it, okay? So anyways, what happens if we do the addition between them? Well, I already have them drawn in here in green. So imagine I put them head to tail, just like we usually do addition, right? So look at the green vectors. So the first green vector here going upwards, I don't know if you can see it, that's the 4.3 stretched of the J vector, plus this green vector over here on the top is the I vector stretched out in the opposite direction because there's negative, And then if you think about we're starting at the origin and we're landing in that place, we're getting this u. So therefore, we can call this thing the u. So that's kind of confusing. You might say, well, what's the point? Here's the key thing. If I asked you guys, what is the point over here? Who can tell me the actual coordinates of the point at which the vector u is pointing at? Anyone?
Negative 2.5, positive 4.3.
Perfect. Good job. So if that's the point, then the notation that we sometimes will utilize for u will be either this weird combination version, but that's too much writing. And mathematicians not only are smart, but they also want to be efficient. They're like, okay, that's too much writing for us. So we're going to utilize just the numeric values, and we'll use a comma in the middle. So if we remove the vectors, and we'll say that the very first one we record is always to do with the x's or always to do with the I hat. And the second one we record is always going to be to do with the y value, vertical, which is the j hat. But then if we use brackets like this, doesn't that kind of look like a point? So vector and a point, they're not the same thing. Point does not equal to a vector. So some textbooks will still use the round brackets, but other textbooks will say, well, because we want to make sure that the person who's reading knows that this is not a point, sometimes they utilize square brackets just to indicate. I usually still write the round brackets, it's just easier for me. But what I'd like you to always do to make sure that you know that it's not a point is always name it, okay? So watch out how it's named. So from now on, you will never just record two numbers with a comma in the middle without recording something in front. So if you do mean it to be a point, call it one single capital letter like P for point P. If you mean it to be a vector, then you want to put in front of it a vector letter with a vector symbol. That way you know which one's which. So in both situations, they look like they are identical, but one of them is actually pointing from the origin towards the point, and the second one is an actual point, okay? So why learn this? Because the algebra of this is now super, super easy. Let's do maybe a little quick example over here. So if I asked you to take the vector u that we already have, which is negative 2.5, comma 4.3, and then let's do some other vector. Let's call it vector. Do I have another one up there? Oh, I do have w. Let's do this one. 5, negative 2. So w, negative 5, 2. So when you see the notation of negative 5, comma 2, you're going to pretend it's a point first. You're going to plot the points. So let's do that one in a different color. Yes?
Doesn't it say that w is 5, negative 2, not the other way around?
Yes, it does. Who was that?
Nadine.
Nadine. Thank you. 5, negative 2. Nadine point. Thank you. So I'm going to plot that one. So I'm going to go to the 5 to the right and 2 down and place my point. So let me just move this thing over here. And you're going to now draw arrow from the origin towards this point. This vector that I just drew is vector w. So now the addition between vectors is now super easy. Would not have to utilize any sine law, cosine law, and all the angles. Watch this. If I want to prove to you that this is actually going to be equivalent. So first of all, what I'm going to do is I'm going to grab this vector, w, and you know how we usually add vectors, we do head to tail. Oops, it keeps doing this. Hang on a second. Give myself that one, and then my u vector over here. All right, so head to tail would be something like this. Okay, I'll draw my resultant. Okay, let me draw my resultant. I know it's not most precise, but you'll get the hang of it. So once I have the head to tail resultant, I'm going to take this resultant and place it back on the grid, but at the tail at the origin. Watch this. So tail at the origin, like so. Okay, let's see what it's pointing at. I have other stuff here, so it's confusing. Okay, so it looks like it's pointing 3 and a bit over and 1 and something up. Where is that coming from? If you were to add like components here, notice how I'm using the word components. That's another thing I should say. For a point, we call these coordinates. These two numbers are called coordinates because it's a point. For the vector, we call those two things right here components, even though they look the same in terms of notation, but we use a different word. So if we were to add like components, we would have what is negative 2.5 plus 5. Well, that's 2.5. My answer is not quite the same. I hoped for it to be more accurate. It's my picture. Okay, then the 4.3, so 4.3 plus negative 2. Okay, so 4.3 plus negative 2 is 2.3. So it's supposed to be actually, let me just redraw it. It was supposed to be 2.5, so that's 2 squared, and then 2.3. It's supposed to be actually more like this. Okay, let me just grab that to see if it is just the way I drew it. It's supposed to be right on, and I apologize that it's not. I hoped it was. So it seems like one of my vectors for either the green one, it's either too long. Oh yeah, look at my green one. I kind of went a little bit longer than I had to. Anyways, take my word for it. You could just add the components and you get the addition. No sine law required, no cosine law required, not even SOHCAHTOA is required, right? The only thing you need to do is to remember how to convert it from geometric to algebraic form, which doesn't involve what we did here, using cosine and sine just on a calculator. So you don't have to do calculations or things like that. Okay, so let's make a summary of what we just talked about. So I have a box on the bottom that has all the formulas you might need. And notice how I have here a blank version for 3 dimensions. We'll come back to that on another day. So I have 2 dimensions. So what does it mean by R2? So we basically think of R as real numbers. So all the real numbers that you can think of, meaning we have integers, we have fractions, we have irrational numbers like pi, numbers that go on forever without any repetition or termination of the decimals, right? So if you think about it as real numbers, it's like on your number line, all the x values or x-axis, all the values on this number line is going to be represented by the R as real numbers. When you see R with a 2 on it, R with a 2 on it is a short way of saying that you have not just the x-axis, but you also have the y-axis. And then when you see R3, it just means that now you're in 3 dimensions. And actually, the way I drew it at the beginning is not the usual orientation that we do. We usually put the x-axis pointing out towards you, y to the side, and z up. Don't ask me why, but you can always rotate it if you wish. It's not a big deal as long as they're all at 90 degrees. Okay, so that's what it says here. Vectors in R2 just means vectors in 2 dimensions. And then we'll do another day vectors in 3D. And the convention is to use these specific letters of the alphabet, I, J, K, for the basis vectors that are in the directions of the X, Y, Z axes. We usually use letters A, B, C to represent the actual component values. So in the formulas, because I don't want to say this has to be a 5 or that's a 6, I want to use general letters. So we'll use ABC, the beginning of the alphabet, for the component constant numbers. And then we're going to use Greek letters, alpha, beta, gamma. So alpha, beta, and gamma for direction angles. I'll talk about that one when we do 3D, so don't worry about it right now, okay? So here are the formulas. So you already saw me write down this version with using I hat and J hat. This was the version that I had over here, where I said that U was equal to negative 2.5 of I. So we stretched the I vector here, but moved it in the other direction. And then we had 4.3. So that's that version. What is that version called? We call it that, sometimes we call it the linear combination form, or we just say we're using the basis vectors. So anything along those lines. So I can say it's also linear combination. Why linear combination? Because there is no exponents anywhere here. Combination just means it's like adding like terms or not like terms. They're just terms within it. Then if we just drop the I and J so that we don't have to keep writing, you know, those vector symbols, the hat and hat for the unit vectors. If we just say anything to do with X direction is going to be in front of a comma, and everything after the direction is going to be, after the comma is going to be to do with the vertical direction, we're going to put it after the comma without the actual vectors. This looks like a point, but remember, if you have a name in front, you'll know whether it's a vector or a point, okay? So this form is called the component form. But how do you get this form if you're given an angle and the magnitude? So the R here represents the magnitude itself. So R is like the radius. If you want to think about it, R is the radius or magnitude. So do you remember how we did cosine and sine before? So that's exactly what I did up here. So this was the radius. The radius of this was 5. So remember, this is the radius of a circle, or the size of the vector, size 5. And then horizontally, it was to do with cosine of the full angle of rotation from positive x-axis. And then for vertical, it was always to do with sine. Okay, so that's exactly the formula that's summarized over here for you, so you can use it. And then to find out the size, if you were trying to convert back, so let's say you were given this and you want to convert back, which I forgot to do. So let's go back up here. So over here, we already converted this one. So I'll record negative 2.5 I hat plus 4.3 J hat, or it was negative 2.5 comma 4.3, this version. So this is linear combination form, and this is component form. Notice I'm not saying coordinate form because it's not a point, it's components that we use. And now if I wanted to convert this one back to this, how do we do that? Well, you would think about it as if you were to draw this. We already had it drawn as 5 over 2 down, right? So 5 over this way, 2 down this way. We want to convert to the magnitude and the angle. So how do we do that? Magnitude is going to be found by Pythagorean theorem. And so you'll have to find this question mark. You're going to say it is 5 squared plus 2 squared, because that's the sides of the triangle that is being created here. And so this will be square root of 25 plus 4. What's 25 plus 4? 29. That's correct. Okay, and so here you would say it is square root of 29, comma, what is the angle? The angle that we want to quote is this full rotation all the way over. So I want to first of all find this angle, let me call it alpha. Okay, and that one you would use tan of opposite over adjacent inside this right triangle. So I would do this quickly, tan inverse of 2 over 5. I get roughly 22 degrees. So who can tell me what is the rotation that goes almost all the way around the full circle, this rotation in yellow, from the positive x-axis? Anyone?
338 degrees.
That's right. So this theta, let's call that one the theta, is going to be And how did you find it, Renee?
Just 360 minus 22.
That's right. So 360 is like a full revolution minus the 22 degrees. Okay. And so if you were to put that over here, you'll say 338 degrees. So this format where you have a magnitude and direction, it was kind of like our geometric version, where we had magnitude and then direction. Go ahead.
My sister's in the waiting room.
Oh. What happened? Thank you for letting me know. Probably dinged, but I didn't hear it. So just to prove to you that going back and forth works the same way. So if I wanted to go back again this way to get 5 and -2, watch this. You would type in 29 square root and then cosine 338. You won't get it precisely 5 because this 338 is rounded, comma, and then type in root 29 and then sine of 338. Do you get roughly this back? I'd like you to verify. Type on your calculator, put in square root of 29, press equal, so you have that number, then times cosine of 338. I'm getting 4.993 something. So it's not exactly 5 because that angle was rounded. So do you see how you can easily go back and forth, back and forth? So for you to be able to convert to the algebraic form, it's just to use a specific formula. Remembering that cosine is for the x, sine is for the y. You know what's an easy way to remember? Think alphabetically. C comes first, then S comes second. So cos first, then sine, okay? And then to go the other route is just Pythagorean and to do the TOA on it. And that's what is being summarized in this, chart right here. So here's the formula how to do conversion to component form. But if you wanted to go back, you use Pythagorean theorem and tan inverse. Okay? All right. To make sure that you guys got it, can you tell me what is vector A that is provided in this linear combination form? And notice when I took this from a textbook, they are not using the hats. You don't have to. If we use I in the future, is implied that it's a unit vector. So I prefer to put a little hat on it so that it's really clear that it's a size 1. So if I wanted to put it into Cartesian coordinates or scalar coordinates, I actually prefer, instead of this word, because to me coordinate means like point, I'd prefer to say component form. It would be just numbers. Who can tell me what they would be? In the x direction is I, which is -4, stretch, comma. In the y direction, which is the j vector, it is the 3. That's it. Okay. Polar coordinates, let's draw this picture to find out the angle. So -4, up 3, draw the point, connect it from the origin. We want to know this length. To find this length, we need the triangle. So this is size 3, this is size 4. So question mark is square root of 3 squared plus 4 squared. Who would like to tell me the solution of that?
5.
It is exactly square root of 25, which is 5. Okay, and then if I wanted to find the angle here before I find this theta rotation, I need to do alpha first. So what is alpha? Alpha will be tan inverse of 3/4, opposite over adjacent. Who can tell me that answer first? The alpha part first? Participate.
Your 3 sort of looks like a 2.
3/4, there we go. What is the answer for alpha?
37.
37. And so if I wanted to say what is my my theta, let me just move this down. So what is my theta, which is the rotation from positive x-axis, what would you say? think straight line. Straight line is 180 degrees, and we have part of that straight line is already 37. So what's the other part?
143 degrees.
143 degrees. And so if you wanted to talk about the magnitude versus the direction version, and this specific direction is the math way. Okay, it's going to be magnitude of 5, 143 degrees. And you would name this to be a vector as well. Okay, then if you wanted to convert it to quadrant and the physics, so these right here, this is for physics class. Oops, physics with PH. Okay, you would have to predefine and say you're going to make an assumption. North is up. Assume north is up. And so we can say the size of that one would be, let me switch the colors. Okay, so what would be this angle over here, this red one? Because that's the one that we want to quote away from north. This one over here. Anyone?
53.
53. So then you would say north, west, and 53 in the middle, right? So if you wanted to quote it in compass bearing, you would say it is 5 units. And then in square brackets, we would say north 53 degrees west. You've seen this notation before. And then if you wanted to say true north, like bearing, so for that one, we want to quote the rotation from here all the way around. Isn't that weird that math and physics, they conflict with each other? But that's okay. You just need to know all of them to make sure that it's just another way of quoting the same direction. So if you go all the way around, what is this green rotation? So what is 360 minus 53? So 360 minus 53. This is for the true bearing. This is for compass. Okay, who has an answer for this one? 307. Very good. And so if you wanted to put it over here, you would say this A is 5 units and then it's 307. And I would say beside this true bearing, just because otherwise it kind of looks like this version over here. So for this one, I would definitely say that this is to do with math angle and here to do with the bearing. That way you'll have some idea how to distinguish between the two. Okay, so let's do another one going the other way. So we have V here. You're told 7 units, and this time it's south. So let me just give myself more space and just move everything I've done so far to the bottom. We have south, 35 west. That means it goes this way like this, 35 away, and size 7. So if I wanted to quote this in true bearing, I want the angle that goes like so from the north line. 0 degrees is over here. Who can tell me what that one would be? 7 units with what angle?
$215.
215 is correct. So 215 is found by taking 180, which is a straight line, plus the 35. Okay, so you'd say 215. And again, I will just specify to make sure that we're clear. This is quoting it like a physics person. So if this was to do with in your physics class, you would be doing it from the y-axis this way, clockwise. So this is from y-axis and clockwise. But if you did it with a math way, so let's switch the color. So let's do blue. V would be equal to 7, comma. And then we want to quote it from the x-axis counterclockwise. From x-axis And please don't think that mathematicians are just out to lunch. I already explained to you the reasoning behind for math choices. I don't know why physics choices made the choice that way. Probably because it's physics is more of an application type of a field where it relates specifically to navigation, and navigation is always to do the north, and the way we orient our maps is north is up, not to the side. So I kind of get both situations, okay? So this is counter.
Would it be 235 degrees?
Clockwise. And what did you say? It would be 235. How did you find this?
Okay, so I did 90 minus 35, and then I just added that to 180.
Very good. Okay. Or you could say 360 minus 90 minus 35 if you wanted to, right? 360 minus the 90 minus 35. What did you say what the answer was again? 235, is that what you said?
Yeah.
235, yeah. Okay, and so this 235 is going to be making it super easy for us to do the conversion to the other side. So let's do it. So you're going to say that is going to be 7 cosine of this angle, comma 7 sine of this angle. And just type it into your calculators. Okay, watch this. 7 cosine of this math angle, because that math angle is going to give us all the negatives that we might need. So it says it's negative 4.02 roughly. Okay, and then 7 sine of 235 is negative 5.73 roughly. And if you actually look at my picture, I know I didn't draw it very precisely, but basically it's saying you're going left 4 units and down almost 6 units. Okay, and that's very easy conversion. And now that you have this one, this last one is just another way of writing it. It's my least favorite version of recording it. You would say negative 4.02 with I minus 5.73 with J. Any questions about this? This is the lesson. Okay, let's see the time. Did I cover everything I wanted? So there are 2 more conversions back and forth that we could do. We can always come back to that, or we don't need to. I think there's certain things in the homework that would be relating about points instead of just a single letter. You know how every single one of these, I just used a single letter to indicate the vector. But what if you had random points on a grid? For example, this example here, 4, 3. So 4, 3, let me draw it. And notice how these are points. How do I know it's point? Because in front of it, there is just a single letter. It's capitalized. There is no vector symbol on it. So this I'm going to draw as a point. So 4, 3, 1, 2, 3, 4, and up 3. This is point A. And then point B is negative 1. So negative 1, up 1, B. If I wanted to find out vector that is pointing from A to B, how do I do that? Well, I first of all draw it. And then remember, to find out the vector, it is about taking that vector and moving it to the origin. Can you tell me what the vector would be? So once again, you can think about it as the I and J. So you can think, okay, I is pointing this way, but I'm going in the opposite direction. 1, 2, 3, 4, 5. So it's like I have negative 5I on this, right? And then if you think this is my J going up, but I actually went down 1, 2, down, so negative 2J. And so this would be equivalent to saying negative 5I plus or minus 2J, or negative 5, negative 2. Now I did it with a picture here, but what's a way to get from here straight to this, guys? What do you notice? Where this -5 came from if you didn't have a picture to look at and count squares?
Miss Kate,
Mm-hmm.
on the you wrote -2i.
-2i over here. Who said that?
Veronica?
Veronica, thank you. Veronica point. Thanks. Okay, so back to my question. If you didn't have a grid and if you don't want to draw precisely and then precisely move it without changing orientation and the length, which is kind of hard to do, you want to be able to do it algebraically. So how do you think we're getting this -5 from these numbers of the points? Anyone? Okay, that's okay if you don't know. Let's start off with what we did for proofs. AB, let's go from A to origin and origin to point B. Do you agree that AB is the same thing as going to the origin first? So imagine going from point A to the origin and then revisiting back to point B. Well, negative OA and OB is equivalent to this above. So why did I start with origin? Well, we just talked about up top. Where was it? I said that if the vector is oriented in such a way that the tail is at the origin, the head that's pointing at the point actually is going to look identical to the vector itself, as long as the tail is at the origin. So back to this. If you can get your vectors to be origin first and then they'll point, so notice how it's origin, then A, origin, then B, then you can actually say the exact same values. So I would say that O to A is a vector 4, 3 exactly. And vector OB is a vector -1, 1. So it's now no longer points, they're now vectors. And so if you were to put those in, don't forget the negative in front. If you put those in, and then when you're adding vectors, remember what it actually means. This means that there is a negative in front of 4i hat plus 3j hat and plus -1i hat plus 1j hat. And then you just deal with it with like algebra. You would distribute your negative like so. And then you're going to be collecting like terms. We talked about how to add vectors when you have like terms, right? There's one here. And so this is the same as that one. And so that would be -5i. And this one, -3 plus 1 would be -2j. And that's exactly the components I have up here. I, in the future, always skip this. Because if you look at it, you can see that you want to basically do the same thing with this version, the component form. You want to basically distribute the negative on the inside and add things that are like in front of the comma, they go together. So if you were to think, there's a negative on the 4, so that's -4, plus a -1. That gives me -5, right? Then if I think about the other one, I have negative on the 3 plus 1. So -3 plus 1 is this -2. So in the future, you could just do this addition without resorting to i's and j's. But it is important to do it only with vectors. You cannot be doing that with points, because how do you add points? To add points, you cannot do such a thing. There's no such thing as adding a point to another point, because it's kind of, I don't know, there's no math to be done with points. But with vectors, we can put them head to tail, and actually do additions. And with algebraic way, you can actually find the components much easier without doing a picture. Okay, so the summary of this is up here. If I have a general point x1, y1 for the A, and general point B, x2, y2, to find what we call the position vector. So if we were to reposition AB to be at origin, to be with tail at origin, those of you who joined and you're not AP students, I will be able to see the fact that you came in for attendance. You can just continue working on your own. You don't have to stick around. Okay, so reposition AB with the tail at the origin. So suppose origin is over here. Oh, remember how we can place origin anywhere? And then I'm going to draw this vector and reposition it. So once you reposition it, let's say it's now pointing at a different point. Let's call this point P. So if AB is going to be now equal to this OP, because it's the same vector, it's just repositioned somewhere else, then to find this vector, it's always going to be equal to OB minus OA. Always. Meaning, let me just make sure that people are coming in here. Which will be x2 minus x1, comma, y2 minus y1. So that's in general, and this is an example. And that's it. I'm going to stop here. Questions? I know this is brand new, it's weird, and possibly even confusing, but once you start using it, you'll be okay. So the notation here is, I don't like that it's overlapping with points, but I guess we ran out of symbols to use, and so we have to use similar notation, but just always watch out for the context. Always label things so that you know that you're working with a point versus a vector. All right.